Alright, so today I'm gonna be explaining this important paper with the title struct2vec, Learning Node Representations from Structural Identity. This paper, which is for 8 years ago, is still very important. Structural identity is a concept of symmetry in which network nodes are identified according to the network structure and their relationship to other nodes. Structural identity has been studied in theory and practice over the past decades, but only recently has it been addressed with representational learning techniques. So this work presents struct2vec, a novel and flexible framework for learning latent representations for structural identity of nodes. Struct2vec uses a hierarchy to measure node similarity at different scales and constructs a multi-layer graph to encode structural similarities and generate structural context for nodes. You see an example of two nodes U and V here that are structurally similar. Look at the degree of them. Degree of them is 5 and 4 connected to 3 and 2. Triangles. So connected to the rest of the network by two nodes, but very far apart in the network. So degree node U has node U has degree 5 and node V has degree 4. Node U is connected to 3 triangles. Node V is connected to 3 triangles. 1, 2, 3. I mean the neighborhood of that. So you see they are very much similar to each other structurally. So the most common practical approach to determine the structural identity of nodes are based on distances or recursions. You know, these methods Node2vec, deepwalk that I've explained in different videos, they tend to fail in structural equivalence tasks. So that's a good motivation for this paper as well. So we implement an instance of struct2vec and show its potential through experiments, and they compare it with Node2vec and deepwalk. So we have 4 steps in this algorithm. First, we determine the structural similarity between each vertex pair in the graph for different neighborhood sizes. Then we construct a weighted multi-layer graph where all nodes are present in every layer. Then we use the multi-layer graph to generate context for each node. And finally, apply the technique to learn latent representation from a context given by the sequence of nodes, for example, skipgram. So the most important part of this paper is here, this very interesting recursion. So this f sub k of uv, this is the structural distance between node u and v when we have k-hop neighborhoods. And g here is the distance between the ordered degree sequences. So this definition makes f a non-decreasing in k. So this is a very good property. And also using the ring at distance k forces comparison between the degree sequences of nodes that are the same distance from U and V. Of course, nowadays we don't do such a thing. We have very advanced graph kernels. So this paper is for 8 years ago, but it's still, you will see that it has some good ideas still relevant today. So it finds the optimal alignment between the two sequences given a distance function for the elements dtw, which is dynamic time warping in this paper, finds the optimal assignment between the two sequences. And it matches element A and B such that the sum of distances between matched elements is minimized. So we construct a multi-layer weighted graph. Each layer is formed by this weighted undirected complete graph. Then the edge weights between layers are defined like this. So now we want to generate context for nodes. Given that it will stay in the current layer, the probability of stepping from node U to node V in layer K is given by this probability. And it has a normalization factor as well. So the random walk will prefer to step onto nodes that are structurally more similar to the current vertex, avoiding nodes that have very little structure similar with it. Note that every time the walker steps within a layer, it includes the current vertex as part of its context, independent of the layer. Thus, a vertex may have a given context in layer K, but have a subset of this context at layer K plus 1. So we use hierarchical softmax, where conditional symbols are calculated using a tree of binary classifiers. So it looks like this. C is just a binary classifier present in every node in the tree. So you see the distance distribution between node pairs in the latent space for the mirrored karate network learned by both struct2vec and struct2vec.